Welcome everybody in AP Chemistry series. Today we'll start with section 8.3, which is all about weak acid and base equilibria. In the previous video, we covered the strong acid and bases, and today we're going to cover the weak ones. As we're going to learn, the concept of weak indicates to dissociating partially. So if you just put the weak acid or base in water, they will partially dissociate. So what does this mean? Or what are the examples? How can I do this process? How can I calculate the pH? What are the acids and bases that are considered to be weak? So first of all, I just want to show you, let's say, different examples of weak acids. So let's start with an example of HF. It's considered as a weak acid. HCN. We have CH3COOH. And by the way, guys, the acids or the organic acids that end up with COOH considered to be weak ones. Let's go to example of weak bases like NH3 and H2OH, considered as a weak base too. So my target today, I would split this one here into two sections. I need to calculate the pH for both weak acid and weak base. So how can I do this? And now let's start. Let's take an example. Now suppose that we have 0.1 molar of HF solution, which is an acid. My question is how to calculate the pH of this solution, and just keep in mind the value of Ka. If you just remember, it's the acid dissociation constant, and it equals to 1.2 times 10 to the power negative 5. And you just can see that the values of Ka's for weak acids generally less than 1. And this tells me that partial dissociation of the acid because it's weak, as we said. So the first step, if you want to calculate the pH for an acid, let's start with the first equation. We have the acid. It started to dissociate with water. Since it's an acid, it has to produce hydronium ion, which is H3O+, in addition to the conjugate base, which is F negative. If you are unable to write the conjugate bases or conjugate acids, you can watch the section 8.1 of the playlist video in here. We're going to apply the Rice table. So we started with the reaction. And since the initial concentration of HF is 0.1, then I have to say it's 0.1 here. We don't care about water. And these guys will be 0 because we have initial time at that point. The change will be negative X because, it will start to dissociate. And it's not the same as the strong acid. In the strong acids, we usually said 0.1 minus 0.1 because it's fully dissociate. But here we don't say, we just say negative or minus X. The products will be increasing, so we have to say plus X. And for the equilibrium thing, it will be 0.1 minus X. We just combine the two magnitudes here together, and two magnitudes here and here. So we say 0 plus X is going to be X. 0 plus X is equal to X. All right. So generally, we are going to calculate the pH, right? So if I know the concentration of H3O+, I'll be able to calculate the pH and everybody will be happy. So how can I do this process? I have to say, all right, so we're given the value of Ka, which is here, the beautiful Ka, the small value of Ka that tells me the reaction is partially dissociating. And for sure, don't forget the reversible errors that tells you that you have an equilibrium thing. All right, so I have to say the value of Ka has an expression, which is the concentration of H3O+, which is the product of reactant. It's the same thing that we covered in Unit 7. And then we'll divide it over the concentration of the original acid. And since the value of Ka is given to us, it's equal to 1.2 times 10 to the power negative 5. The value of H3O and F negative are equal, so I have to say they're X squared over the original molarity of HF. Okay, I just want to tell you something about HF. We're going to neglect this part, minus X, because you don't need to solve a quadratic equation in your AP exam. So we neglect this value in here. Okay, we neglect it. And so we just put the value of 0.1 down below. And if you just apply some algebra, if you take the negative log for the concentration of H3O plus, you will end up with a pH of 2.96. So this is the pH of a weak acid. You can see that the pH actually is not that low, and this tells me that this is a weak acid for sure. Now let's take almost the same numbers of a weak base. Suppose that the weak base here is 0.1 molar of NH3, which is considered as a weak base. I need to calculate the pH, and we suppose that the value of Kb, since we're dealing with base, we use Kb, not Ka, just keep in mind, is equal to the same number, which is 1.2 times 10 to the power negative 5. So first of all, you have to write the rice table. So you have to say NH3. It dissolves in water and it produces OH negative because, you know, like this is a base, plus the conjugate acid, NH4 plus. And as we said, so this is R. The initial value for NH3 was 0.1. And for water, we don't care about it. So it's going to be 0 for the conjugate things. And for the change, it's going to be negative x because, as we said, it partially dissociate. Here we have to say plus x. Here we have to say plus x. And at equilibrium, we got 0.1 minus x. And here we have to say plus x plus x. All right, so far we almost have the same steps, and we're going to apply the Kb. The Kb is equal to 1.2 by 10 to the power negative 5. And the values here are equal to x times x equals x squared over 0.1. We neglect this part, so we have to say 0.1, and then we'll end up with a value of x, which is the same one, 0.001095 molar. But just keep in mind the value of x here represents the concentration of OH negative, and the same as the NH4. So I cannot calculate the pH directly from this value. So I have to calculate the pOH first. All right, the pOH is equal to negative log the concentration of 0.00195.96. And if I need the calculation of the pH, and suppose that the temperature was held at 25 degrees Celsius, I can say for T minus 2.96, and it equals to 11.04. And now, guys, pause the video and read this question carefully and try it in your own. All right, so the question says the pH of a 0.02 molar of CH3COOH, which is the vinegar solution, is in which of the following ranges? All right, so we're given the value of Ka. Since the value of Ka is less than 1, then I can consider that this is a weak acid for sure. Now I have to say, okay, CH3COOH, it dissociates in water, and then we have reversible errors because it's weak acid. It's partially dissociating. The acid produces H3O plus in addition to the conjugate base. How can I determine the conjugate base? All right, so here we are just remove the hydrogen, and you will end up with CH3COO and negative sign. We apply the rice. Okay, so the initial value of CH3COOH is equal to 0.02. All right, the initials are zeros. The change is going to be minus x. For H3O plus is going to be plus x, here plus x. Combine the magnesiums together, so it's going to be 0.02 minus x, and here we have plus x plus x. Right, the expression of Ka is equal to the concentration of H3O plus multiplied by the concentration of acetate CH3COO negative over the real concentration of the acid. 1.8 times 10 to the power negative 5. Just put x squared. We neglect this magnitude, so it's going to be 0.02. You apply some math, you will end up with the value of 0.0006. And since the x here represents the concentration of H3O plus, you can see here, then the value of pH is going to be the negative log of 0.0006, and the answer is equal to 3.22. So your answer is going to be, answer is C.